In this short video, we provide a proof of the fundamental theorem calculus. Basically, fundamental theorem calculus links together what looks like two really distinct concepts, that of differential calculus and integral calculus. So what we have in calculus is basically addressing two primary issues. One is the derivative, which is the instantaneous rate of change, and integration, which is the cumulative sum of a varying phenomenon. So in the case of a derivative, the derivative is the instantaneous rate of change. It's also the slope of the tangent line. And therefore, when the derivative is greater than 0, the function is increasing. When the derivative is less than 0, the function is decreasing. When it's equal to 0, it's easy to reach a max or a min. On the other hand, the equivalent sum of a varying phenomena, we take and add up, basically, the little rectangles. So f of x represents the height of the rectangle. And dx is the width of the rectangle. So the total area is the sum of all these little areas, and we take it to a limit, we get what's called the integral, or the definite integral from a to b of the area under this curve. So what fundamental calculus says is that these two issues of differentiation and integration are connected. Basically, that differentiation would undo integration in this sense that if I have the integral of a function going from the lower limit of a to an upper limit of x, a variable, then I'm going to get a function. In particular, it's going to be a differentiable function. So all I need is a continuous function inside the integrand, and out of this I get a differential function. And not only that, the derivative does nothing more than undo the integration. So this is what we mean by differentiating undoing integration. And on the other hand, if on the other hand I have an integral from a to b, and inside the integral I have a derivative of some function, then the integration undoes that derivative, and I evaluate it by the upper value of the function minus the lower value of the function. So let's see how do you prove this. So if f is a continuous function on ab, then we're saying that the derivative of the integral of from a to x of f of t dt is equal to f of x, namely the derivative undoing the function, undoing the integration. So how do we do this? Well, we start out with the left-hand side and just plug in the definition of what we mean by derivative, which is the change in the y value to a change in the x value, basically. So here the x is the upper limit is going from x plus h from x to x plus h. And we have this difference in the numerator. Well, that difference can be written by the property of definite integrals as a single integral from x to a. Now let's see, what does this numerator look like? Well, the numerator is really the area under a curve of the f of x function from x to x plus h. Well, since f of x is continuous on this interval, we have, by the extreme value theorem, that the function can take on some lower value to some larger value. That is, a function doesn't skip any values, and it has some small number to some big number it goes to. Therefore, this integral can be bounded above by the little m, and below by the little m, and above by the capital M. And so then we get the whole term that we wanted is just lower bounded by m and upper bounded by capital M. However, as h goes to 0, the m, capital M and little m coalesce, and they become one value, right? Because the function is continuous. So therefore, by the squeeze theorem, we see that this limit is nothing more than the function we want. That is, we've shown that the derivative of an integration undoes the integration. Now, how about part 2? Part 2 says, assume we have a continuous function again, and let f of x be any antiderivative of the f of x function, little f of x function. Then we're saying that the integral from a to b of f of x is evaluated by taking the antiderivative function, evaluating the upper limit, minus the antiderivative function, evaluating the lower limit. So how do we do this? So we start now with the right-hand side and partition the interval from a to b into these little subintervals, from x0 equal a to xn equal b. And therefore we can write the difference of the function f of b minus f of a as these sums of n differences. And now let's look at what each of these differences look like. Well, again, we have a continuous function, and by the mean value theorem, it says we have not only a function, but a differentiable function, because the f of x is differentiable. So if x is continuous and differentiable, then there is at least one value of c in the interval from a to b, such that the derivative is equal to the secant line, basically. Or there is a point in the interval whose derivative is exactly the slope of the secant line. So then we can write these differences as this derivative times delta x, or f of c, little f of c, because f prime is nothing more than f of c. So then we have what we wanted to prove, that all these little summations are nothing more than exactly what we want. And therefore, we have shown that the integration undoes the differentiation. Now, what's important to remember, though, is that the fundamental theory of calculus is silent on finding the antiderivative. It says if you know an antiderivative, then yes, you can evaluate a definite integral. But it does not tell us how to find it. And so the challenging part of integration is this issue of finding an antiderivative. So again, the fundamental theory of calculus is very, very important, because it connects the two ideas of differential calculus, saying that derivative undoes integration, and integral calculus, where the integration undoes a differentiation. Anyway, thank you very much.